จะเปลี่ยนภาษา All right, so now that we have talked about the cache consistency sample questions, we'll resume our lecture and now talk about VLIW and the GPU, right? So you might have heard something about this GPU thing, right? If you play computer games like I do, you actually have been using it so far. But let's look back and step back a little bit and see how it actually get to the point where we are, right? So a quick recap on midterm. We talk about out of order instruction dispatch, right? You have out of order scheduling where we would move dependent instruction out of the way and you issue instruction further ahead of time, right? And we use a bunch of structure to support that, like a future file and the architectural register file, right? So the benefit is faster. It can tolerate the latency of instruction that can take a while to finish. And the key component is that you have the reservation station that acts like a Windows that operation can be dispatched, right? Whenever they're ready, right? And then you have a bunch of things to reorder all your assembly code that you finish back to the same order as a program, right? This is basically to support precise exception. You also have things like register aliasing table or the rename table to make sure that you can deal with register renaming, where register ID is then renamed to the reservation station entry ID, right? And you then have to tag the value and the valid bits. This is done to eliminate the right after read and right after write dependence, right? And this enable even more performance, right? And then we talk about the Tomasulo algorithm, which is basically how do we schedule things out of order at all, right? So basically, if reservation station is available, right? You check the source and see if the source is available, and then you dispatch whenever you have the instruction that becomes valid for the input, right? You dispatch the operation. And then you have the common data bus that keeps listening to whenever an operation finished, then it forward the data to your inputs, right? And then with that, right? With that, you have things like the downside of out-of-order processor where, first of all, it requires a large instruction windows and it can be complex, right? And costly to do all the scheduling and perform dependency checking and support data parallelism. So back in the day, when hardware is actually limited, so you don't have every single resource and small transistor to put in this logic, right? People have come up with other techniques. For example, the idea called decoupled access execute try to address this problem where out of order scaling is too complex back in the day to implement, right? So the idea of this paper is to allow data access and the data execution to be decoupled across two different instruction streams, right? Basically, the idea is I have a queue that's visible to the ISA. Now, the ISA can now control this hardware queue. And then you send in instruction to access the data, and then an instruction as a separate stream to compute the data you access, right? So this paper is proposed in ISCA 1982, right? And it's followed up into a journal in 1984, right? Back in the day where we still care about journal, right? I mean, in this case, the compiler would be the one responsible for generating these two instruction streams. And they use control flow instruction to synchronize between the two streams, right? So here is the overall architecture. Again, you have instruction in the memory, right? So instruction is here. And you also have the data, right? Inside the memory. Basically, that's like one Neumann architecture, right? You then have the two type of instruction, execute instruction and access instruction. This is basically compute, And this is memory related instruction. When you have memory related instruction, the access processor process that by putting the request. So there are two things, right? You have the register file where you can put in the right request to write new data into the memory. And then you can also read the data from the memory and then send it to this queue. This is access queue. This is execute queue. So basically you have new data coming in, right? Data coming in here. Then you have a totally different set of instructions, which is a compute instruction, and say, hey, I want this address, and then I want to add it with someone else, for example. You perform execution, you put the data in the register file, and then you basically forward this data back to the access processor, right? So this everything here acts like a synchronization point, right? This allows the two processor to only handle what they're designed to do. The left processor, the access processor, anything that has to go with accessing the data. Once I have the data, I feed that into the queue. The queue will be processed by the execute processor, which then say, okay, now let's do an add, let's do a multiply, right? And then the one who's responsible for scaling everything here is the compiler. The compiler would generate, right? The compiler basically generate the two instruction stream, right? Over here, it would generate the two instruction stream, right? To make sure everything is done correctly, right? Based on the program. So you have let's say a C program. The compiler would generate the A stream and the E stream, and then feed it to this particular processor, and then it will process both the access and execute in a way that it imitates the outer order scheduling, because now it becomes more of the data flow machine, right? So the benefit is obviously this lower the complexity because the execute stream can run ahead of the access stream. The access stream can also run ahead of the execute stream depending on who is faster at each point, right? But the problem is then you have to actually design a compiler. So this can be pretty complex, right? And then we haven't really mentioned branch, right? So when you have code branch, that becomes another synchronization point. You have to figure out, okay, I'm not taking the branch, and what do I do with my instruction stream that I fetch, right? So that's the trade-off of these type of processor. And then if you talk about fetching instruction, right? In out-of-order processor, there's so many ready instruction, right? And the scheduler has a choice of what instruction do I issue. So what are the ideal choices? For example, you can think of the data flow graph, right? And figure out who might become the bottleneck in the future. For example, if I have a add instruction that generate a data for many other future instruction, then I would try to process that instruction that has a lot of consumer first, right? But the question is, what if there are multiple types of ALU that's available, right? I have like 2 adder and 4 multipliers, for example, then what do I do? So the question to ponder in modern processor, there's a lot of ALUs available, right? And our design goal should always, right, always be to maximize the utilization, right? So in order to maximize utilization, the problem is how do we do that, right? I have a bunch of ALUs, and you need to figure out what are the dependency between each instruction, and then figure out if I have 2 adders, can I schedule these 2 add instruction to each of the adder, and will that cause any problems, right? So let's say I have 2 adders like this, right? Can I put instruction 1 here? And then can I put instruction 2 here in parallel, right? In parallel, so that they both do the add. I need to make sure that instruction 1 and instruction 2 doesn't have any dependency, right? It doesn't have any dependency, so they can be operate independently of each other, right? And then to figure out independent instruction, then you need a big window so that you have a lot of available instruction, right? So the cost of maintaining a large instruction window can be high, So that's the problem. The problem is if I want to detect independent instruction that can feed into like tons and tons of ALU, the cost to maintain that gets high. So one solution is, well, why don't we rely on the compiler to help us, right? So this is kind of like the concept, well, not the primary concept behind VLIW, but it's proposed to address the earlier problem where um, um, I need to maintain a big windows to be able to like dispatch a bunch of parallel instruction. So VLIW will stand for very large instruction word. So what is that, right? So you think of out of order processor, instructions are scheduled dynamically, and they try to maximize the ALU utilization and try to hopefully retire the older instruction and make sure dependent instructions are prioritized, right? But the first downside is we have limited instruction windows, and then the design can be complex, right? Because you need a bunch of transistors to do the sorting and to make sure that we can look into, okay, do I have the data ready to send to the ALU? So another different idea is why don't we rely on a compiler to perform some part of the instruction scheduling? Because fundamentally, right, instruction that are ordered in the memory are already ordered by the compiler, right? So a bunch of things that a compiler can do to your code is to reorganize some of the instruction to make sure they can get faster when you run it, right? So these are something like decode elimination, constant propagation, get rid of constant and propagate it everywhere, get rid of code that will never get run, try to unroll your loop to make it faster, right? So these are something simple that compiler can do, but the more complex task that compiler can do is actually try to figure out, for example, if I have 5 ALUs, can I try to create an instruction stream that allow you to send all those 5 execute operation at the same time, right? So a quick recap on this concept of direct acyclic graph. So the fundamentally direct acyclic graph is basically a graph that has direction and there's no cycle, right? Graph that have direction that has no cycle. For example, if I have things like prerequisite for your class, right? These are DAC, these are direct acyclic graph. And this is applicable because when you talk about handling prerequisites, it's the same as the data flow graph, right? This is going to look similar to the data flow graph where you look at operations like operation like an add, it generate output for a multiply, right? Then another adder generate another input for the multiply, which generate input for my adder, which then generate an input for the multiply. So these are direct acyclic graph. I need to finish these two add first, right? Followed by this, followed by this, followed by this. So we can use this concept to represent our instruction, right? To our instruction using graph. So basically, if I can have like say add, I guess the first add, the second add, right? And multiply and add, for example, right? And then there's a dependency between these two instructions. Basically, this becomes I first add the two numbers together, generate the input for the multiply. And then there's a separate force add, that is add 1, right? Add 2. And then add 4, right? Has nothing to do with the other two adds. And then we have the multiply here, which they will all generate output for someone else, right? But this can be some way to represent your program, right? Your program can be represented using this format. And then another quick recap on instruction word is instruction word include opcodes and operands. So I asked the what if question. What if you pack multiple instruction into one? What if you pack multiple instruction into one? For example, I know I have two adders, so my instruction would contain. So let's say I have two adders in my ALU. So ALU has two adders, right? So now my instruction can contain add one, the first add, right? And then the second add. This is the concept behind VLIW. Basically, I have one single instruction, but now I basically pack two operations into this one single instruction. So the benefit is, well, scheduling decisions are now done by the compiler, right? Through the compiler, I perform scheduling. I put those two add together. Compiler knows that the two add are independent of each other. I can put them in. And I pre-pack this set of instructions that are dependent and can be scheduled at the same time, right? So the idea behind VLIW is I will create multiple function units with the ALU with multiple types. And then I use the compiler to figure out where are the independent instructions. And then I provide this scheduling. Each group or each bundle are then executed in lockstep, right? When I said the word execute in lockstep means that they execute together. The instruction within each group are then statically aligned to directly feed into the correct functional unit. To the correct functional units. If we cannot figure out something should go into, say, the second adder, I put no ops. I don't do anything. So this is the idea behind the VLIW processor, which is, I guess, also proposed in ISCA 1983, right? ELI stands for enormously long word instruction. I put a bunch of instructions together, right? So the high-level design is something like this. For example, right, I have my instruction. This is a memory that has instruction, right? And then down here, I have the, so my ALU, right, would look like this. I have one adder. I have a load unit, right? I have a multiplier. And I have the thing that control data movement, right? So in that case, I need to make sure my compiler can then have the first instruction being in the add, the second being the load, the third being the multiply, and the fourth being the move instruction. And they will be fed directly to each processing element. Again, the downside here is instruction sent to the processing element has to be the correct type. For example, over here, it had to be the adder. Okay, that does look like a multiply, my bad. This thing is just an adder, right? It basically can do an add, but if I feed in the multiply instruction, it will not work. So this is the multiplier, right? And this is the load store unit, right? So my instruction pointed to by the PC or the program counter has to be aligned this way with the correct type, right? With the correct type. For those of you who've been working on a GPU so far, you might have seen something familiar here under the notion of SIMD or SIMT, right? But this is generally kind of the same concept. The discussion with VLIW is the trade-off, right? Is you can now use every single ALU if your program allow you to fit everything in. If your program allows the compiler to fit in all those instructions into that one line, awesome, you get a lot of performance improvement. Complexity is then who designed the compiler. So the compiler gets complex, right? Compiler gets complex. We are doing much better these day and age in 2022, but back in the day in 1980s, so in the 1980s where VLIW was introduced, this is a really, really, really hard problem. Also, what if that's some branches, right? How do you recover from that? What if the program is not parallelizable? That means you're screwed, right? Because you cannot have one add, like for example, you look at earlier slide here, every single instruction need to have one add, one multiply, one data access, and one data movement. if you cannot build your program this way, then you will not get the full benefit of VLIW. So it means that the program has to be parallelizable in the exact same way, right? This is pretty restrictive, but there are modern VLIW processor that actually got discontinued recently, right? If you heard of IA64 or Intel Itanium, like that's not fully VLIW, but it does have the EPIC instruction set that can have a bunch of independent instruction to put into the bundle, right? And then it would allow the dependency to be extract from this bundle of application. It does fail due to backward compatibility problem, right? Market already adapt to AMD 64, but fundamentally you can use the compiler to fix this problem, right? So that's kind of the story behind VLIW. I guess, which also get followed up into IA64, right? But if you look at something that looks similar, this guy looks almost like VLIW. So now let's just take a quick break before we dive further into the concept behind the GPU. And in the meantime, I'll answer any question through the chat. All right. So let me first stop the recording so we have a bunch of parts for this lecture.